All right, let's go ahead and begin. So last week we covered floating point numbers. We talked about how the computer stores numbers in its system, okay, using bits, and because there's only a finite amount of bits, it can only represent approximations of a lot of numbers, and if two numbers are very similar in value, it won't be able to distinguish between them, right? So when we saw large numbers that were similar in value, even though they were like one whole integer apart, it couldn't distinguish between them. Today we'll start talking about numeric methods, okay? And numeric methods are a class of methods that we employ on the computer to help us solve problems, okay? So, you know, in math, you learned algebra, okay? Somewhere in your mathematical career, you learned algebra and you learned how to manipulate values. You'd say this letter X represents an unknown value, okay? So this letter X represents some kind of unknown value, and if I have it in this equation, I can, you know, move things around, square things, take things to powers or whatever, and solve for this mystery unknown value, okay? The computer does not have any logical sense of that, okay? It doesn't understand math, it doesn't understand calculus, or at least not at this level computer, okay? And so, but we still want to be able to solve equations. We still want to be able to, you know, take integrals and things like that. And so what a numeric method will do is it will basically be a set of instructions, an algorithm that takes advantage of what the computer can do. Okay, the computer is able to add numbers together. It's able to multiply. It's able to do computations very quickly. And so we can use the strength of the computer, which is solving these computations, for solving maybe some algebraic type problems, okay? So numeric methods, these are kind of methods, algorithms or instructions that the computer can follow rapidly, that the computer can follow to give us good estimates of values, okay? And generally, so, you know, traditional approach would use, algebra, maybe, or calculus or something to solve for unknown values, okay? Instead, we will employ some kind of numeric method to, give us a good estimate of this, okay? I'll just write computers can't do algebra, okay? Okay, instead, we can use a numeric method. And by starting off, we're going to start off with some simple numeric methods today, and we'll just get up to not even that complex of methods, okay? But we're going to just kind of introduce these concepts of numeric methods, because this is these numeric methods are going to be things that power a lot of more complex applications, okay? So there's a whole lot of stuff, with machine learning and deep learning and all sorts of stuff that your phone is now able, like, you can take a picture of something and your phone is able to, like, say, oh, there's a dog in there, right? Like, you can later say, like, show me my pictures of dogs, and it will, like, go through your pictures and tell you, like, oh, here's a picture of a dog. That's just a bunch of numeric methods that have been taken to a very powerful level. Okay, we're going to just start off with the basics today. And so our first set of numeric methods is going to be what we call root finding algorithms or root finding methods. Okay, so our first set of numeric methods root finding methods. Okay, and so we have some function f of x, and a root of f of x is the location of x where f of x is equal to 0. Okay, so basically where f of x crosses the x-axis. All right, in algebra, all we would do is we'd set f of x equal to 0 and solve for x. Okay, but again, a computer can't do algebra, right? Equal to 0 and solve for x. Okay, instead computers can't do algebra, so we'll use we will estimate the root with the numeric method instead. Okay, and numeric methods are almost always iterative in nature. Okay, algorithms, and I'll say or instructions. Maybe I'll just say usually iterative. Okay, meaning that you'll start it and then you'll just kind of repeat it over and over and over again. Okay, so our first root finding method. Okay, and we'll call this fixed point iteration. Okay, and we'll say some functions, not all, but some functions have what we call attractive fixed points. Okay, so if I've got some function g, so a fixed point of the function g of x, so if I've got some other function g of x, is where g of x equals x. So when you plug the value into the function, it spits back the same value. Okay, that's a fixed point. So it's basically where g of x crosses the line y equals x. Okay, so visually, it's hard to draw. Okay, so this is y of x, and this is g of x, okay? And this here is a fixed point. Fixed point of g of x. So for example, if g of x equals the square root of x, it has an attractive fixed point. At x equals 1, okay? And what we mean by an attractive fixed point is that you can plug in any value, start off at any value, and if you keep just applying this function, the square root function, it will eventually give you back 1 or something very close to it, okay? So let me just kind of demonstrate this. So I'm going to just pull up the calculator on my computer. All right, and then we can just start off at any value, right? So I can just type in, blah, 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 blah. All right, so I don't know what this is. This is a million, billion, trillion. Is that 1 quadrillion? 447 trillion, 300, no. 1 trillion, 447 billion, okay, whatever. It's a big number, all right? All I have to do is, if I take the square root of this, now we're at 1.2 million. Square root of that gives me 1,096. Square root of that gives me 33. Square root of that gives me 5.75. Square root of that gives me 2.3989. Square root of that is 1.5488. Square root of that is 1.244. And if I just keep taking the square root, my numbers get smaller and smaller and smaller and smaller. And we can see that this will eventually kind of converge to 1. Okay? I can take any other value. I can start off at well, not a negative number, but 0.000087654 or whatever, all right? And I can take the square root of this, and if I keep doing this, then we get closer and closer and closer, and it's 0.9999. So as I take the square root of this, and we can see if I just keep applying this iteratively, I'm going to get to the fixed point x equal to 1, okay? And so this is an example of this square root function has an attractive fixed point, meaning if you just keep applying the function over and over and over to the output every single time, it's going to converge to its fixed point, okay? Not all functions have that, but if we have a function, if we can write a function with an attractive fixed point, then we can take advantage of that, okay? It has an attractive fixed point at x equals 1. This means I can start at any value. I'll say any value greater than 0. And if I continue to apply the function, to its output, we will get x equals 1. Okay, so here's our strategy. We have f of x, and we want the roots of f of x, okay? So what we will do is we will rewrite f of x equal to 0 into the form g of x equal to x, okay? So we'll rewrite f of x equal to 0 into the form g of x equals to x, okay? And if g of x, hopefully g of x has an attractive fixed point, okay? And if we can solve for the fixed points of g of x, find the fixed points of g of x, they will be equal to the roots of f of x. Okay, but the warning is not all functions have attractive fixed points. Okay, so there's often many ways to rewrite f of x equal to 0 into g of x equal to x. There are often many ways to write f of x equal to 0 into g of x equal to x. Okay. And not all of them, and not all forms of g of x will have attractive fixed points. Okay, so I'll just use a textbook example. So the scientific programming textbook, chapter 10, we're going to just use, we'll say f of x is equal to log of x minus e to the negative x, okay? And we want roots of f of x, okay? So where does f of x equals 0? Okay, so what I'll do is I'll take f of x, log of x, minus e to the negative x, set that equal to 0, and we're going to just kind of move things around. I've got log of x is equal to e to the negative x, so I'm going to add e to the x both sides, and then I'm going to just raise e to this side and e to this side, and so I get x is equal to e raised to the e of negative x. Okay, and so what I'll do is I'll let g of x equal this part over here. I'll just rewrite it as exp of negative x. Okay, and we will try to find fixed points of g of x. Okay? All right, so we've taken our f of x and we've rewritten it into the form of it being x equal to some function. Okay? There's other ways this could be done, right? There's other ways to rewrite. Okay, so I could have done log of x minus e to the negative x is equal to 0, and I could have just said let's add x to both sides. Okay, and then now I have log of x is minus e to the negative x plus x is equal to x. Okay, and then I would just say, well, let this be g of x. Okay, this will actually not work because there's a property, and this unfortunately does not have a fixed point. That would be an easy solution, right? Another one is I could do I could say, well, let's take, because this is 0, I could just do, let's do x minus this, right? X minus log of x minus e to the negative x is equal to x minus 0, and then which is going to become x, and I got x minus log of x plus e to the negative x. Okay, and I can just say, well, let this be g of x. Okay, and we can try something like that. So there's a lot of often a lot of ways to to do this, and not all of them will have attractive fixed points. But anyway, let's go ahead and we'll just use this one. And the fixed point algorithm is very simple, okay? Okay, just start at some arbitrary value. X0, it doesn't matter, okay? Start at some arbitrary value, X0, and then plug X0 into g of x, okay? You get g of x0, and use that as your next value, x1, okay? And basically, we're going to just say x, the next value of x is equal to g of the current value of x. So xn plus 1 is next iteration, next value of x, or x at time n plus 1, and xn is our kind of our current value of x, x at time n. Okay, so here is some pseudocode. And basically it looks like this. While, and I'm going to just throw in this, because this would run forever, right? So we need a way to kind of stop it. So we're going to say while x old minus x new is greater than some kind of tolerance level, what we will do is we will take our current value, assign it to x old, and we'll say the new value is going to be g of x old, okay? And that's it. 2 lines, 3 lines of code. 4 if you count the closing curly brace. And it's and that's going to be fixed point iteration. So let me just kind of demonstrate this. All right, so we'll do this. Remember, so we wanted to find fixed points of this f of x, log x minus e to the negative x, and what we've done is we've rewritten f of x into g of x equal to x. And so we're going to say g of x is equal to exp of negative x, okay, e to the e of negative x, and then we're going to set that equal to x, find that. All right, so let's go ahead and we'll do this. All right, so g is a function of x, all right, and what it is it's going to be exp of negative x. Right? So the exp function is the e function. So exp of 1 is basically e 2.7182 whatever, right? And exp of 2 and whatever. Okay. So anyway, so this is what we have. And I'm going to just write while the absolute value of x old minus x new. So how much did x old change versus x new? And we're going to say, well, that's greater than some tolerance. What we will do is we will write, take our x new value and assign that to x old. And the new value we're going to use is going to be g of x old, okay? All right, and in order to get this to run, I need to kind of initialize my values. So x old, where should I start? Well, here, let me just kind of demo what this looks like. Okay, so we'll just start off with x old being like 100, okay? And then x new will then be g of x old, okay? So if I just start off with x old being this, here, let me just do this for a second, okay? So I'll say x is going to be g of 100. And I can ask, well, what is x? Oh, well, that gave me 1, okay? Because basically, we're asking, we said e to the e of negative x, right? So e to the negative 100 gives me practically 0, and I have e to the 0 gives me 1, okay? And then we're going to take this, and we're going to plug this back into x of g of x, okay? So we're going to try that. And x is now the value 1.444668, okay? And I can just kind of repeat this process. We'll just replace the old value of x, okay? And so when I plug in 1.44, I get 1.26595. Are you guys able to see this on the screen? Okay. And I'll try this again, and I get 1.32574. I try this again, I get 1.304. And I try it again, and it gives me 1.311. Try it again, I get 1.309. And I keep going, and we can see it kind of bouncing around a little bit. That's fine. And we're getting something 1.3098. We can see the values up here just change ever so slightly as I keep running this. Okay? And we can see it kind of converging here, right? Okay, so right now my value is basically 1.3098. Let's do options, digits equals, let's do like 7, okay? No, okay, it's still that. All right, and let's see, is this a solution to our original, is this a root of our original f of x? So, okay, so our f of x is log of x minus e to the negative x, right up there. So we're going to say, all right, what is log of x minus e to the negative x? And we should get something that's 0, because it's supposed to be a root of this function. And when we plug it in, indeed, we get basically 0, okay? Something, you know, times 10 to the negative 13. Okay, so we have been successful in finding a root of f of x by finding a fixed point of g of x, okay? But anyway, if we wanted to just run this kind of algorithmically, all right? So we'll delete all of that out, and I'll say x new is g of x old. And then let's set our tolerance. Our tolerance, let's do like 10 to the negative 8 or something, okay? Okay, and it's done. And again, what is our x new? 1.3098. And we saw that when we plug that into log minus e to the negative, we get basically 0, okay? So anyway, that is that's fixed point iteration. So I'll go ahead and I'll copy this kind of code chunk in here. And I mean, you can, I don't know how many iterations it runs, but if you wanted to, you could even throw in a print statement to kind of just see how it bounces around. But so we'll go ahead and throw that into your notes. Oh, something. Okay. Is that all right? Any questions on fixed point iteration? All right, and then again, the warning here is g of x may not have an attractive fixed point where you just keep applying the function and it gives you just goes to its location. The rule is if the slope of g of x, the absolute value of the slope, is less than 1, it will kind of converge to its fixed point. Otherwise, it will diverge. Okay, and there's often multiple ways to rewrite f of x equal to 0 into g of x equal to x. All right, let's talk another method. This is the Newton-Raphson method for finding roots. And I'll try to draw this picture, but it's kind of hard. Especially on the... Okay, so let's say... What's going on? Okay, so let's say I have some function that looks like this, okay? And this is our root. So here's my function f of x, okay? This is my root that I want, okay? And this is how it works. We start at arbitrary x0, okay? So I'm going to just say here's x0. We find f of x0. So I'm going to go up. Okay, so here is f of x0 right here. And then I draw a tangent line. Draw a line tangent to basically to the point x and f of x0. Okay, so I'm going to draw a line tangent here, which will go something like this. Okay, and so this is my tangent line, and where it crosses here, that will be my next value. Okay, so where the tangent line crosses the x-axis, that will be my next value, x1. And then we repeat. Okay, and so for the next iteration, I start at x1 and I go up to f of x1. I draw a line tangent to f of x1, and I end up right here. And this value will be x2. At x2, I go up, and I get f of x2. I draw a line tangent to f of x2, and this will give me x3. And so on and so forth, and we're going to converge to something close to the root. Is that okay? Kind of conceptually, we start at a point, we go up to the line, we draw a tangent thing, and we get our next thing. Okay, so basically, what I need to know is where is the next value going to be? Okay, so if I just write this as the next value, xn plus 1, is equal to xn. What is it in relationship to our current value? So if x0 is right here on the line, how did I get over here? I'm going to just subtract off. I'm going to label this triangle. All right, so let's take a look at this kind of this triangle right here. Okay, so if I take a look at that triangle, basically I'm going to just say our current location minus the run. Is that okay? So we're going to just take a look at this triangle, and it's going to be the next value, x1, xn plus 1, is our current value minus whatever length this is down here, the run. Okay, what is the length of the run? Can I figure this out? Okay, well let me say, let's do slope is equal to rise divided by run. Is that okay? And I can rearrange things, and I can say run is equal to rise divided by slope. Is that good? Okay, the rise, what is the rise equal to? The rise is going to be the height, f of xn, basically minus 0, right? Because we started off at 0 and we're going up to f of xn. So that's going to be my rise. And what is the slope at the tangent line? What's the slope here? It's the derivative, f prime at xn. Okay? So this boils down to the next value, xn plus 1 is going to be xn minus xn minus 0 is just f of xn divided by f prime of xn. So this is the Newton-Raphson method for root finding. And it requires that we know the derivative of f, okay? So it requires that we know f prime of x. But that's it. We're going to just do this and do that. Okay, so let's do a simple example. Okay, let's say f of x is equal to x squared minus 4. Okay, so we already know we have roots. Where do we have roots? Roots at where? Where does this thing cross the x-axis? X equals 2 and x equal to negative 2, right? So at x equal 2 and x equal to negative 2, f of x equals 0, and those will be our roots, the roots of the function, okay? But let's go ahead and we'll solve this using Newton-Raphson. So what I'm going to do, let's go ahead and just delete that out. We'll go ahead and clear all of this out. What I'm going to do is I'm going to create a function f. F is going to be a function of x, but this time I'm going to have it return 2 values, okay? So one will be the value, which is going to be x squared minus 4, okay? And then the other will be the derivative, which I'll call f prime. And what is the derivative of x squared minus 4? should be easy, right? 2 times x, okay? And what it's going to return is we're going to just combine these two things. We're going to return the value and the derivative f prime. Okay? So if I plug in, say, f equals 10, it's going to give me back two values, okay? 96 and 20, okay? So at that point in the parabola, the value is 96. 10 squared minus 4 is 96. And the derivative there's a slope of 20, okay? And I can access these by doing like f of x, and I can say give me back the first value, and that will just give me back 96, because it's returning a vector, right? And I can also just subset and say give me back the second value, and it gives me back the slope. So we get the value and we get the slope, okay, by subsetting what we have. Okay, so in how would I write my algorithm in pseudocode? I would have basically the same parts, while basically the absolute value x old minus x new is greater than some tolerance level. We're going to update our things. We'll take our current x new, and that's going to become old for this iteration, and then the new value is going to be x old minus f of x old divided by f prime of x old. And then we close that off. So in our case, I'll just write while the absolute value of x old minus x new is greater than some tolerance. Our current value of x new will become old for the iteration, and then we're going to say x new minus f of x old, and we want the value divided by f of x old divided by the derivative. And that's it. That's the entire algorithm. Okay. Now I have to initialize these things. So I'm going to say x old is, I don't know. We'll start off. I guess we'll start off at 10, and then x new will then be. We'll just go ahead and plug. And I can just. Yeah, we'll just go ahead and plug this in here. Whoops, this needs to be x old. And then we'll say our tolerance is going to be 1e minus 8. Okay, so we'll go ahead and get this started. We'll run our while loop. It's done. Okay, and what is our x new? Our x new is 2, which is exactly what we expected. Okay, so it has successfully found the root. If I gave it a different starting point, say -10, okay, x new is -2, so it gives me the other root. Okay, so I would say it's pretty successful at working. Okay. Go ahead and I'll copy that into your notes. And we'll, okay, so there it is. Different starting locations. Can converge to different roots. Okay. Other problems. It fails if f prime of x is equal to 0. Okay. because basically if you've got something like this, if you know, if xn is 0, it's never going to cross the x-axis, right? So that's an issue. And then you can also end up very far away. If f prime of x is not 0 but close to 0. All right. So if we ended up just ever so slightly off, okay, and our slope was not exactly 0, but ever so slightly at an angle, okay, then you know, we end up xn plus 1 ends up way out there, okay? So that's another issue, okay? And then it's also possible to end up, you know, back at your starting location. Of another iteration, which leads to a loop. Okay, so let's say, like, I don't know, let's say you happened to start here, okay? Let's say for whatever reason you happen to start here, and just the sequence of the algorithm ends up putting you here, and when you end up here, it shoots you back to the location where you started from, okay? And so now you're in this kind of, you're just following the sequence, but because of this weird thing that shoots you far away, you end up back at where you started from, and you end up going through the same locations and things like that, okay? And so that could also happen, right? So there's no guarantee that it's going to work. A lot of times it works, but there's no guarantee that it does. We'll cover more of these algorithms on Friday. I will also release a homework assignment, okay, that starts covering numeric methods and stuff like that, floating point arithmetic, and so you have that to look forward to as well. Okay, we'll see you guys on Friday.